A previous video linked down below went through the development of the first law of thermodynamics, the conservation of energy. The first law basically said heat gets converted to work, work gets converted to heat, but the total internal energy of a system remains constant, where the internal energy, delta U, is the change in heat with the change in work. One problem with the first law is that even though it says energy cannot be created or destroyed, it says nothing about in which direction that energy will flow. Everyone intuitively knows that energy goes from high to low. Water falls downhill. You put an ice cube in a cup of water, it will melt. But there's nothing in the first law saying why that happens. James Clerk Maxwell was aware of this problem, as well as everybody else studying thermodynamics at the time, and he came up with a whimsical thought that he published to basically goad people onto thinking, where he said there was a demon in the middle of every system that just pushed the heat from hot to cold. Obviously, Maxwell and everybody else knew this wasn't the case, but the point was to highlight the fact that the first law was missing a very important component. How does energy flow? This was eventually solved through the work of Nicolas Léonard Sadi Carnot, a French engineer who was trying to design the perfect engine. Although this was a theoretical exercise, it's also obvious that Carnot would be doing this because the whole impetus for developing and studying thermodynamics was to try to create the best steam engine possible to power the Industrial Revolution. So Carnot theorized that his perfect engine would be filled with an incompressible perfect gas that would be used to move a frictionless piston to create work, and that the entire cycle would be done in 4 strokes. This becomes significant. As an expanding gas does PV work, if you look at a plot of pressure versus volume for Carnot's engine, see stroke 1 is an adiabatic expansion from point A to point B at some high temperature. For this step, since it's adiabatic, the heat flow dQ is 0, and the change in internal energy for the first step is therefore equal to the work done. Stroke 2, the second step, is now an isothermal expansion from point B to C. Since it's isothermal, that means the internal energy for the second step is 0, and the heat is exchanged is equal to the work done, minus the work done. The third step, going back to the beginning, would be an adiabatic compression, now at a low temperature, a low heat state, from point C to D. Again, since it's adiabatic, the heat flow for this step would be 0, and the internal energy for this step would be equal to the work performed. And finally, the third step, a return from D to A with an isothermal compression, where isothermal means the internal energy is 0, heat flow is equal to minus the amount of work. So, for the entire cycle, the change in the internal energy, the first law energy, would simply be the sum of the energy from the first step and the second step, plus the third step and the fourth step, or separating it out, the sum of all the various heats of which they were transferred in steps 2 and 4, and all the work where there was work done in each step. Another important factor in here is that the cycle starts at point A, and it does a complete cycle back to point A. That means it began and ended at the same state, so delta U is therefore defined as 0 for the entire cycle. So, you start off with the fact that the internal energy, which is all the heat plus all the work, is equal to 0 for the cycle. And the definition of efficiency, which is work performed divided by energy provided. These two things together, The efficiency would be the work performed, which would be the work in steps 1 plus 2 plus 3 plus 4, divided by the energy provided, which would be Q2, or the high energy reservoir. Since the entire cycle has an internal energy of 0, the sum of the heats is equal to minus the sum of the work. So the efficiency can be rewritten as minus Q high plus Q low divided by Q high, or 1 minus Q low over Q high. And since heat is proportional to but not the same as temperature, you get a Carnot efficiency equal to 1 minus the temperature of the low heat reservoir divided by the temperature of the high heat reservoir. This is useful, but how does it apply to thermodynamics and general systems? I have the definition of the Carnot efficiency. First of all, T low divided by T high has to be a fraction, so the efficiency of any engine, even a perfect engine, has to be less than 100%. This led to Carnot's theorems. 1, since you have a reversible process in a perfect engine, no engine can exist which is more efficient than a perfect engine. Since the efficiency of this perfect engine is less than 1, Carnot's second theorem is that no energy can transfer heat from a high energy reservoir to a low energy reservoir to perform work at 100% efficiency. In other words, for people who had been looking forever and ever for perpetual motion, it simply wasn't possible. You can't have a machine operating at 100% efficiency. This statement that you can't transfer heat at 100% efficiency is the absolute statement of the second law of thermodynamics. However, it's probably not the statement that you are used to hearing. If you look further at the Carnot cycle, heat is proportional to temperature, which means at any given temperature, if you divide the heat by the temperature, you get a constant, which is the heat capacity of the system. If I look at the Carnot cycle, from A to B to C to D between Q high and Q low, that would mean that Q high divided by T high minus Q low divided by T low would have to be 0, since Q is related to C by a constant. This is the definition of a state function. If I'm starting and ending at the same place and the result is 0, I have a state function. That state function is entropy, and it is defined thermodynamically as the integral of the change in heat divided by the change in temperature. This is a fundamental statement that's always true. So the second law was derived through an examination of a perfect engine. A further video, linked below, will examine how the second law is developed and how it affects systems in the real universe. Hope you enjoyed, and thank you for watching.